Yeah, I'm going to talk about including internal tides and gravity waves in global operational ocean models. This is work that I've done with a huge number of people, especially students and postdocs in my group at University of Michigan, as well as collaborators at the Naval Research Lab in the US and a few other places, including also Dimitri Menamenlis, who's done a nice simulation with the MITgcm that we'll be looking at. And it's been funded by the Navy, Naval Research Lab, Office of Naval Research, National Science Foundation, and NASA. So last time I talked about some basics of tidal modeling, and went through a lot of slides. And today I'm going to talk about, there'll be a lot less words, a lot less equations, and more research results. And so last time I left off here, reminding you that tides are resonant. This particular phenomenon here is really more about barotropic tides, but as you'll see, I think it actually does feed back onto internal tides, as I'll talk about right now. So today's talk, which I think will be shorter than the first one, will be about research results. And the first research result I'll talk about, I kind of added this in the other day. It's not in the chapter, but I decided it might be fun to throw this in. There actually is a back effect of shelf tides upon open ocean tides. So traditionally, people think of coastal ocean tides as being driven by the deep ocean. Of course, there's a lot of truth to that, but they think of the deep ocean as this infinite reservoir pushing on some bay, but there's actually a back effect of the shelf onto the open ocean. So I published a few papers on this with Chris Garrett and others, same Garrett as the Garrett and Monk internal wave spectrum. So this is one of the analytical models that we used. We imagined a 1D system where you had a deep ocean of depth H1 and a shelf of depth H2, and this is looking down on it. You could imagine the shelf being less wide. But Chris is the kind of guy that thought that even this was too complicated, solving the shallow water equations in this system. You know, you can do it analytically, but it was a little complicated. So he said, let's make an even simpler model. It's hard to imagine a simpler model of the open ocean tides connected to the coastal tides than this. You have a big mass on a spring and a little mass on a spring, shelf, deep ocean. And what we showed in this simple model, and basically we showed the same thing in this more complicated shallow water model, is that even if the shelf has a very small mass or volume, whatever you want to say, if it is near resonance, it's surprising how much the motion of this little guy here can affect the motion of this guy. Quite a strong effect, which means that you might expect that the shelf tides can affect the open ocean tides. So then we showed that with a realistic tide model in the following way. So we said, let's have a realistic global barotropic tide model. And this is what the amplitude of the M2 tide looks like in the Hudson Strait, which is the most important place in the world for barotropic tides. There's a lot of tidal dissipation taking place in here. There's something like 40 spheredrups of water going in here just from the tides. So it's really a whopping big place for tides. So a lot of tidal dissipation. This is what the tidal amplitude looks like. So then if you just say, well, what the heck, you know, you can do this in a numerical model. Let's pretend the world is exactly the way it is, except you can barely see here, you block the Hudson Strait. That's all you do. So you block the Hudson Strait and you run the model again. This is the difference in the tidal amplitudes around the globe from a blocked Hudson Strait experiment to an unblocked Hudson Strait experiment. You can see that it affects the tides around the entire globe, according to this model. So I gave this talk at a birthday celebration for Chris Garrett. Walter Monk was there. Some of you have probably heard of him. And he said, oh, you could use this for geophysical warfare. I thought that was an interesting comment. So anyway, so it has this global effect. And so later, near the end of the talk, I'll show you how we're trying to take advantage of this back effect to improve the barotropic tides in our much bigger HYCOM simulation, and therefore hopefully the internal tides. Oh, so I said that this is the most important place in the world. So I went around and blocked all the places in the world that have big tides. And here's, for instance, the Northwest European Shelf, i.e. the English Channel. It also has a significant effect, but the biggest effect by far was from this one. In fact, blocking the Hudson Strait increases the global tidal amplitude by 12%, just blocking that one place. So other places also matter, but that's the one that matters the most. Okay, so now getting back to the big simulations where we have winds plus tides in them, many layers, big computers. And then in the end, near the end, I'll get back to how that idea I just told you about is being used in such big simulations. So first I'm going to show you the first HYCOM wind plus tide simulations that we published, a few simple results from that. So I told you this last time, you may or may not remember, that when Harper Simmons and I did the first global internal tide simulations, for simplicity we only had tidal forcing. Since we didn't have atmospheric forcing, we had a uniform stratification everywhere, just taken out of the subtropics. So what we did here is we ran HYCOM with those conditions. 2 layers, tidal forcing, constant stratification. What happens is you get these big internal tides down here in the polar regions, which people like Laurie Padman, who study internal tides down there, said were artificially high. So that's why I went ahead and did this contrast. So this is what the sorry, I forgot to mention, this is the internal tide sea surface height amplitude of M2, which you can pick out by picking out the steric part of the model. That's essentially the baroclinic part. So then you run it under realistic conditions, so now the stratification in the polar regions isn't the same as in the subtropics as in the simplified run. It's different. And you see that you get a lot less internal tide signal down there. So we were happy about that. I showed that to Laurie. He said that was good. So that's the first simple point, that just simply putting the internal tides in a model that has realistic forcing is going to give you a realistic horizontally varying stratification, and you get some first order effects, changes in certain areas. Okay, simple result number 1. So another thing I just kind of alluded to is that we like to separate the different components of the flow by looking at the steric and non-steric height. So this is the non-steric sea surface height in region of the Southwest Pacific. There's New Zealand, there's Australia. And the non-steric sea surface height is dominated by these large-scale features you may remember are from the barotropic tides, from the movie I showed last time, these big blobs that move around as Kelvin waves. So the non-steric sea surface height, mostly what you're seeing other things. There's other things there, not just tides, but the tides are the strongest motion. Now in the steric sea surface height, you're seeing mesoscale eddies. And this texture right here, which you're going to see in a minute, changes at much higher frequency. That's the sea surface height signature of the internal tides, which can be measured by satellite altimeters. Therefore, it's important for SWAT, as we just heard a moment ago. The altimetry community is very interested in this right now. So this texture here, which moves at high frequency, as you'll see in a second, is internal tides. These are eddies. They move at low frequency, and there's the barotropic tides. So I'll show you a movie of that. That's today's movie. These are the movie of the steric and non-steric sea surface height in a HYCOM simulation that has all that stuff in it together. Okay, so the non-steric sea surface height is this is around Hawaii, not the same region as that previous plot. But the non-steric sea surface height is dominated by high frequency, rapidly propagating, very fast phase speed, about 200 meters a second, large-scale barotropic tides. Then the steric sea surface height, you have stuff that's high frequency, but much slower than this, because the phase speed of internal tides is much as, it's a few meters a second, not a few hundred. And then you have the low frequency eddies, which on this time scale in this movie are, much more steady looking. They do evolve, but much more slowly. So I like this movie because it shows you have your low frequency geostrophic eddies, which we all know and love. I love them too. My PhD thesis was not on tides, it was on these things. So you have your eddies, you have your high frequency internal tides, and then you have your high frequency barotropic tides. Now again, coastal models have had all these things in there for a lot longer than global models, so I just want to make that point again, that global models are behind in getting all these things in there. But now we're doing it. That's what this talks about. Okay, so just to make that point again, if you look at the sea surface height, tidal elevation, M2 amplitudes and phases in a model like Gary Egbert's TPXO model, which is used a lot in the tidal community, you see the amplitudes and phase lines. We talked about that last time. And you don't see any small scales in it because it's just a barotropic tide model. But if you look at it in the HYCOM simulations, especially if you pick out a particular region and zoom in on it, you can see that superimposed on the large scales is this small scale texture. You see it in the phase lines as well. Look at how the phase lines have a lot of kinks in them compared to here. So again, these things can be seen in models, and they can be seen, as I showed last time, in altimetry data. So it's kind of a funny thing that internal tides and waves are much more interesting in a sense at depth. They have much bigger signals, but currently we don't have instruments that can see those things globally. So if you want to get a global look at these things, then you use things like altimetry, which means you're looking at the sea surface height, where the signature of these things is still detectable, but it's much smaller than it is at the surface. All right, so one other, I think this is the last result I'm showing from those first simple runs. So here's a section of zonal velocity through Hawaii along 156 West. And here is a snapshot, and here is a mean. And so as well as zonal velocity, we're also looking at the isopycnals. So the isopycnals in the snapshot, look at how you have all this structure, which in the 24-hour mean is eliminated. Okay, so you have a smoother structure in the 25-hour mean, which is, of course, what most model output until relatively recently does. You put out daily, or at least global models. Global models tend to put out daily averages, and an hourly snapshot has a lot more structure when you put in these tides. Okay, and you can see a similar thing in the velocity. It's actually, I think, easier to see in the isopycnals. Okay, so now what we're going to do, having shown those simple things like, okay, the tides really are in there, you can see visually things happening at high frequencies. So let's now compare the model to data, first compared to altimetry. So here's one of the first papers we wrote that was really focused on comparing the model. The first few papers we wrote just said, wow, we have these things in a global model, and here's a few pictures. Then we started, and a lot of this stuff about all the technical stuff you had to do. But then we started writing papers comparing it to data. So here's our first comparison to altimetry. So here's, again, the M2 sea surface height, amplitudes, and phases in a highly accurate altimeter constrained model from Gary Egbert at Oregon State, and then from an early HYCOM simulation. So, I hope you'll agree with me. You can look at this and you can see clearly they're modeling the same thing. Clearly a lot of the features are similar, but you don't have to look too hard to see places where there's quantitative differences. See how this is not the same quantitatively as that. Okay? Now, I'll show near the end that I'll show the error in this HYCOM simulation, then I'll show you how I can use a Kalman filter to greatly reduce that error. No, sorry, this was for M2, the largest semi-diurnal tide. Just quickly, here's what you see for the largest diurnal tide. So again, it's the same kind of story. That's clearly they're very similar, but quantitatively you can see differences in, well, pretty much any region you look. So that's the barotropic tide. Now note that the scale of the barotropic tide for M2, say, is 70 centimeters. Now, one way to get the internal tide out of this is you do a spatial high-pass filter, because you may recall from things I showed last time. The internal tides have a lot shorter spatial scales, so you can separate the internal tide part of the signal from the larger and larger scale barotropic tide with a high-pass filter. So that is what we do here. All right. So here we have the internal tide from HYCOM as determined by high-passing that total sea surface height amplitude. And it looks tracky, and that's because it is tracky. It's actually, what we do is we take the amplitude and interpolate it onto the Topex Poseidon tracks, and then we do the high pass along the tracks. And the reason we do that is because the best available data of internal tides from altimeter is not from constrained hydrodynamic models like Gary Egbert's, because those are purely barotropic. It's from actual analysis of raw long-track altimeter data. So here's the long-track altimeter data from Richard Ray himself, the guru of such analyses, the same Richard Ray who did that first amazing analysis I showed last time, showing you can see the things in altimetry. He's a co-author on this paper. So here's the long-track analysis from him globally, and here's what you have in HYCOM. And again, what I would say is I hope you'll agree with me that with the possible exception of the Atlantic, you're forgetting that, I would say in the Pacific, where you have more hotspots of generation, you see a lot of gross similarities, but you can see differences. Again, I'd say the Atlantic is, to my eye at least, looks the most different. So what we did in these boxes here is we computed the average amplitudes in the model compared to the data, and they agreed to within 20% or so, so we were pretty happy with that. Now I'll show you later, one thing we didn't even realize when we did this paper is that the amplitude that you compute actually depends on the duration of your record. We didn't even realize that when we did this calculation. But anyway, with that caveat aside, 20% we were pretty happy. And again, this is for M2, the largest semi-diurnal tide. A more interesting comparison in some ways is seen here when you compare the K1 internal tide. So K1 is the largest diurnal tide. And so starting with the Pacific and the Indian Ocean, let's just look at these hotspots here for a second. And again, you can kind of see gross similarities. And that's where a lot of the internal tide activity is. And when you take averages over this box, you get about 20%. So then you might say, well, gee, how come the real data is showing all this activity in strong boundary current regions, which is present in the model, absent in the model? We're almost positive, and Richard Ray's on this paper, and he did not argue with it, that this is a rare case where the data is wrong and the model is right. And so let me explain why that is. So first of all, simple theory that we all learned in graduate school tells us that the frequency of internal tides has to be between F and N. So for K1, what that means is that you can't have propagating internal tides poleward of 30 degrees, okay, because K1 actually has a frequency of exactly one sidereal day, and that you use the sidereal day when you calculate F. So you take twice times the sine of the latitude. Where does the sine of the latitude equal a half? So that 2 times that equals 1, well, 30 degrees. So the model is actually not giving you propagating internal tides poleward of 30 degrees. It is behaving according to that fundamental relation. What's going on in the data then? Well, one trick about internal tides and altimetry that makes it hard is that, remember that you're sampling something that happens every, in this case, day, in the case of semi-diurnal tides, twice per day, and you're sampling that every 10 days. So if you think about it, if you have a high-frequency phenomena like this, and you're sampling it rarely, what that means is you alias it into much longer periods. And they all alias into the broadband mesoscale continuum, which means that effectively it's very, very difficult to pick out, to separate internal tides and mesoscale eddies in the real altimeter data because the internal tides are aliased. So when you're in places where the mesoscale eddies are really strong, it makes it even harder. So this is just noise. This is mesoscale eddies pretending to look like internal tides. Okay? And we weren't the first to realize the altimeter had this problem, of course, but I think this is the perhaps one of the more dramatic demonstrations of it. All right, so going back to the M2 internal tides, when you look at plots like this, you can say, oh, look, the patterns are pretty similar if I take an average, okay? But what if you really zero in on these features and look at them carefully? How close is the model to the data there? And here we're looking at data where we trust it more. It doesn't have those, well, you always have these aliasing problems, but you can pick the coherent stuff out if you're careful, and if you don't have a lot of mesoscale eddies, then we mostly trust it. So here you can see the HYCOM versus altimeter plotted wiggle against wiggle. And so, I hope I'm not being too pessimistic, but for a comparison like that, I wouldn't use this model, our HYCOM model, for operational purposes when you look at that. There are places where it looks like we're doing pretty well, but there's plenty of places where we're not. Okay, so if you want to remove internal tides operationally for SWAT, most of us agree so far you would treat models like HYCOM as a process study model, a very expensive one. But probably to get the most accurate internal tides, you should just do analysis of the altimeter data itself, with someone like Richard Ray. We hope to improve upon that, but that comes later. Okay, so having shown comparisons to altimetry, let's look now at comparisons to moorings. So here's a comparison of M2 current semi-major axis in Greenwich fades versus depth for a particular current meter record in the North Pacific position given up there in the title. So here's the depth. Here's the semi-major axis changing with depth. Two different ways of measuring it from the model. Won't get into that too much. The observations, which I say current meter, these are actually ADCP data. And so you can see that I think there's some amount of skill in tracking the changes in the semi-major axis with depth, which is essentially the magnitude of the velocity, and also some degree of skill in picking out the changes in phase with depth. Okay, so we're happy about that. I'll be honest and tell you, though, that this particular plot, we cherry-picked a location where the model was doing quite well. It's not always doing this well. So when you look at thousands of current meter records, as we did, and then you take an average of the kinetic energy, you can make plots like this. So here's the kinetic energy versus depth in HYCOM versus observations, starting first with M2 because it's the largest and most important. You can see in both cases that a kinetic energy is surface intensified, as motions often are in the ocean. There are some bottom trap motions, but a lot of times things are surface trapped. And there's some skill in the model tracking that. There's less skill in some of the other constituents, but we have some plausible reasons for why that might be. So when we ran these first HYCOM simulations, we weren't thinking about all the analyses we might do with them. We weren't really thinking about doing this kind of analysis, and someone said, why don't you do this kind of analysis on a run that was already done? Now in this run, we only saved 1 month of 3D model output because it's expensive to store all this stuff. And so we only had 1 month to analyze, and we also put in the 8 largest tidal constituents. And if you do that, unfortunately, there's another constituent called K2, which is very close to this one, which means that it pollutes the analysis of this. Your record isn't long enough to separate them. You have the same problem here with K1, which is close to P1, so there's those analysis problems. And then furthermore, another thing is that the wave drag, which I'll talk more about later, is frequency dependent, but we tuned this model for the M2 tides, and so that means that the diurnal tides are overdamped, which I think might explain why you can see there's this general tendency for the model to have less energy than in the observations. So it's a hard game to do everything well in this, but based on the reviews of this where they did legitimately complain about the analysis being contaminated, we've done something in the model that you can't do in the real world. We don't force it by as many constituents anymore. Now we've removed some of the smaller ones so that the frequencies are well enough separated that you don't have to have such a long run to separate them out. One other thing I should mention, by the way, is that this plot and the previous one really shows that tidal currents have a lot of vertical structure. And what's interesting about that is that operationally, a lot of people remove tidal energy from current meter records using Gary Egbert's barotropic tide model. So I'm hoping that someday, once we're a little further along with this model, convince people that it's good, people will start actually using baroclinic models to detide current meters, because barotropic models, there's only so far you can go with that. The real signal in the ocean isn't barotropic. Okay, here's a quick comparison of energy fluxes in HYCOM versus some moorings in the Pacific that have very high vertical resolution. Again, I tend not to do Taylor diagrams and that kind of stuff with these comparisons, because I think we're a little bit in our infancy to do something so sophisticated, but by my eye, it looks pretty good for most of them, with one exception. Another reason we don't tend to do super sophisticated analysis is that if you look at the comparison to historical moorings, which have much sparser vertical coverage, the agreement's not as good as that. So this is actually as good as we can get. These are modern moorings that have really high vertical coverage. I'll talk more about them later. Okay, so I mentioned how we were the first to show that models like this that have atmospheric forcing that gives you near inertial waves, tidal forcing gives you internal tides, enough resolution to give you non-interactions, give you a Garrett-Monk spectrum, or at least a partial Garrett-Monk spectrum. And this is the paper where we showed that. So it's a global model, but we're just looking in this place in the Pacific with a few moorings, these 7, which are laid out like this. Obviously, we don't have to go through all of them, but just picking out this one, we're looking at kinetic energy, F. So here's the near inertial waves, which are wind-driven. These are the semi-diurnal tides right in here. There's diurnal activity in some of these, not all of them. And if you look at this one, it's fairly typical. The mooring is in red, and that follows the Garrett-Monk omega to the -2 prediction shown in this dashed line. And then as far as the model goes, when you increase the horizontal resolution from 1/12th degree in blue to 1/25th degree in green, you still peter out at some point. The spectrum starts to die out, but you get closer over a wider range before you have those problems. So you get a better spectrum with higher resolution. And here is a paper that was published yesterday by my now former grad student Anna Savage, where she used 1/25th degree HYCOM and this new 1/48th degree MIT run, and she compared the dynamic height variance frequency spectra in these models versus McLane profilers. So that's the same ones I alluded to a moment ago. What happens with the McLane profiler is you put a mooring in the water, and instead of having the instruments being fixed, you have them crawl up and down. And so if they crawl up and down and then you do a lot of interpolating in space and the vertical coordinate, you can essentially, you can map it down to like 2-meter resolution. It's pretty impressive stuff. And so, so you have virtually continuous, with the caveat that it was interpolated, but virtually continuous data in the vertical. And high frequency sampling in time. It's very, very hard to do that. These 9 McLane profiler records we got from Matthew Alford are almost the only ones we know of where you have high resolution in the vertical and in time. We look at this frequency spectra. One of you noted the other day that right under the tides, between about 1 and 5 days, there's a pretty persistent pattern where the models have less energy than the data, so there's something funny going on between 1 and 5 days we don't understand. But out here you have the mesoscale low frequency continuum. Here you have the semidiurnal and diurnal tidal peaks. And here you have the high frequency continuum, the Garrett-Monk spectrum that we're all so interested in now. And generally speaking, what you can see looking at this, the HYCOM in blue does not do as well as the MITgcm in orange. And so I'll admit this is a little frustrating to me because we've done so much work with HYCOM, tuning it, and it's been around longer. We published a lot more and blah, blah, all that stuff. But I think this is one of those cases, where resolution really does win the day. So the MIT models have more resolution, and that just really helps out here. So we're starting to get some of that internal gravity wave continuum. The reason the dynamic height signal is so interesting is that's similar, it's just not the same depth range, as steric sea surface height, which means that this is the signal that you're going to see in SWAT. Except in SWAT, it's going to be temporally aliased. So here's another comparison with the McLane profilers, a paper in preparation by my African colleague that I told you about the other day. So here what we're doing is a vertical wave number spectrum. And this is the Garrett-Monk prediction, m to the minus 2. And the McLane profiler, you can see, has a kind of an m to the minus 2 spectrum over usually more than a decade. Very, very impressive instrument. And you can see that both models, the MITgcm and the HYCOM model, tend to peter out in the vertical wave number spectrum. So they fall more rapidly. They're supposed to go like this, and they're falling more rapidly than that. So the data tends to have a similar slope as the Garrett-Monk prediction. The models tend to drop off. So I'm kind of proud of this plot because, to be honest, I've been to SWAT meetings where people show the MIT model, look at how great it is, and here's something where it fails. Okay, you have to show where models fail. And the vertical wave number spectra is not as good as it should be. The reason for that is pretty simple. There's 90 levels, which sounds like a lot, but if you use the rule of thumb that you need 8 points, per wavelength, you're only going to get 10 vertical modes. You're only going to get a decade of spectrum if you're lucky. And this observed spectrum is going over almost 2 decades, and so it's just impossible. And that has implications for mixing because, of course, the Richardson number criterion is written in terms of the vertical wave numbers. So if we want to eventually get these models to the point where you can really talk about mixing, then you want to follow that vertical wave number spectrum as far as you can. Now here's what happens with that same thing if you look at vertical wave number and frequency, which is the way internal wave observationalists tend to like to look at things. So this is frequency, and that's vertical wave number, and that's the McLane profiler, and those are the two models. And so one of the things you should note from this is that there's a symmetry. There's a symmetry around this, and that essentially means that there's as much energy propagating upwards as downwards, which is something that the internal wave observationalists always like to talk about. But you can also see how in these relatively high vertical wave numbers, there's a lot of energy in the data, which neither model is capturing. So again, that's why it dies off in these plots that I showed you here. So this paper will be submitted soon, and it'll be a very comprehensive look at kinetic energy spectra in these two models in the internal wave band in many regions. Okay, so then one more comparison to moorings. You can say, well, all right, I'll sacrifice the vertical resolution that you get from these modern McLane moorings, which are really impressive instruments, and I'll go back to the historical mooring database where you have a lot more instruments. So one of my grad students is working on this right now. So there's something like 1,600 records here. And I showed you some results from his, analysis was one of the very first plots I showed last time of the temperature spectra in the MIT model, getting better with increased resolution. So here's something where he looks at thousands of locations, and I can't even see. You can see it better than me, I think. Yes, okay. So this is the MIT 1/12th model. This is the 1/24th. This is the 1/48th. So resolution is increasing this way. We're integrating the variance in low frequencies where the resolution makes some difference, in diurnal and semi-diurnal frequencies where the resolution makes some difference. But where the resolution really makes a difference is the supertidal frequencies, in other words, the Garrett-Monk continuum. So when you have low resolution, the model's all on this side of the line. It's under energetic. But by the time you get up to 148, it's more like that, okay? So you can see that the energy has increased as you go up. One thing that I find a little bit sad about plots like this is look at all the scatter that you have there. These are actually log axes. So, we've done a lot of comparisons like this, and it's a bit of a bummer that you get a lot of scatter on a log-log plot, but anyway, that's what we get. So this is showing that when you look at thousands of locations, you tend to do a better job with higher resolution than you do with lower resolution. We have a similar plot for HYCOM, but it doesn't, HYCOM tends to be a little more this way because, again, the resolution's not as much. And here's one last plot on comparison with moorings. So I'm pretty pleased with this one. This is another thing in preparation. So here what we're doing, working with Dimitri with this big MIT simulations and some people at University of Toronto. What we're doing is we're taking the global MIT simulation and then we're using that to boundary force a little box in the MIT, and in that box we're cranking up the resolution a lot. Okay, so here we're doing the vertical wave number spectrum, which again matters a lot for mixing of neutral density variance. So that's, overturns in the, eventually in the real world leads to overturns in density. And then here we're looking at horizontal kinetic energy. So these are the Garrett-Monk predictions, which as I showed earlier, the real data McLanes tend to follow. We'll eventually do these experiments somewhere where there is a McLane instrument. But the blue is when you have 2-kilometer resolution and 87 levels, which is similar to the MIT Global 148 simulation. Now, if you crank up the vertical resolution by a factor of 3 to 261 levels, to the red, then this spectrum moves up this much. If you crank up the horizontal resolution down to 250 meters, the spectrum moves up this much. And if you do both together, which is very expensive, then you crank it up this much. Now, so I'm pleased that we're able to get that much closer to this, to that slope, like this. But I don't know whether that's good enough for mixing yet. I'm not sure. But at least it shows the potential of using a global model to force a regional model, and you crank up the resolution in there, vertical and horizontal, and the spectrum gets better. That's ongoing work. Okay, comparisons with internal wave theory. So here's from our first paper showing, again, for the first time that such spectra exist in such models. So here's the horizontal wave number and frequency spectra. I'm not going to talk about these insets, so ignore those. Just look at these. I showed the dispersion relation last time. It's omega squared equals f squared plus the eigenspeed squared times the wave number squared. And so you can plot these lines. And you might wonder, why are there 2 lines for each vertical mode? 2 for 1, 2 for 2, 2 for 3. And the reason is that we're computing these over a box where both f and n vary. Okay, so the theory is for assuming that f and n are not varying in horizontally. But in this model, they are, and so that's why you get a range if you compute the extremes over the whole box. But anyway, so you have energy along this continuum, this vertical mode 1, and when you increase the resolution, you have more energy along that continuum. So energy, more energy. This is all supertidal energy. Okay, so this is beyond the tides. The tidal peaks are here, right there. The peaks are right in the dispersion relations, just where they're supposed to be. There's the near inertial peak, tidal peak. That's what the nonlinear actions in the model are producing, is the Garrett-Monk spectrum out here. Partial Garrett-Monk spectrum. We're not all the way there. Okay, so that was for kinetic energy. Then this paper that was published yesterday does it for sea surface height in many regions, and also in both the MIT model and the HYCOM model. So here's HYCOM, and here's the MITgcm, which has a really high resolution. And so looking at either one, this one fills out more. This one fills out more as resolution increases. And there's even a phenomenon, I'm going to make a confession here, that when my graduate student showed me these plots at first, it was right before a SWAT meeting. And I decided not to show it because I didn't understand what the heck is going on with this. But she said, well, that's just aliasing. And then we realized in the end she was right. So I find this pretty amazing, that we're actually now with these global models, we have aliasing in the models. Hourly output is not enough. If you put out snapshots every hour, the problem is there's energy faster than an hour, and so it gets aliased in. So boom, boom, the model's aliased. So now some of these regional simulations of the MIT model, they're saving every 10 minutes. Of course, one could save averages, like we would in a current meter. Okay, now a little bit about wave drag and tidal energetics. So first I'll talk about the need for wave drag in simpler barotropic tide models. So this is from the first paper I published on tides back when I was a young postdoc. So there's this multiplicative factor, this tuning factor on the wave drag. This is the observed level of globally integrated available potential energy. So that's the energy of the elevations at the surface going up and down. You get that from altimeter derived models. And then here's the potential energy in the model as a function of that tuning factor. And then while we're at it, let's show the kinetic energy too. So basically what it's showing is that if you crank up the drag, the energy goes down. So it's not a very surprising result. But anyway, you need to show it. And so then you can see if you look at the error of the model against observations, that's plotted here. If you have too much energy, you have a large error. If you have too little energy, you have a relatively large error. And right about where you hit the observed value is where you get your minimum and your error. So not too surprisingly, if you put a wave drag in your model, it's going to affect how large the motions are, so you're going to have to tune it to get about the right amplitude. That's for barotropic tides. So here's what the dissipation looks like in these big, expensive HYCOM simulations. I won't go through all 4 of these plots, but the wave drag tends to dissipate over features such as the Mid-Atlantic Ridge, because we have this spatially varying wave drag that depends on the topography according to theories of internal wave generation. And the bottom drag tends to dissipate energy in coastal areas where the velocities are really large. Okay, so I'm just showing you that, things that kind of make sense. This paper here goes into far more detail on the energy budgets if you're interested. There's actually a lot of interesting stuff in there. This is a favorite of mine. So takes a little bit of explaining. So here I'm showing global maps of M2 internal tide, seas over site amplitudes, and HYCOM simulations with different drag scenarios and comparing it to altimetry. So here's the real world, and then here's a bunch of HYCOM simulations that don't have drag. So ever since we've been doing these kind of simulations, I've had people argue with me, even sometimes my own collaborators. That's fine, you can do that. And they say you're double counting if you put in a wave drag in a simulation where you're actually resolving some of the spectrum. So according to that logic, you shouldn't put wave drag in such models, but if you don't put wave drag in such models, these are the kind of fields you get. So notice that the internal tide energy is larger and spreads out farther than it does in the altimetry. Okay. In this simulation here, what we did is we cranked up the quadratic drag along the shells by a factor of 100, and we were basically saying that if you presume the energy is dissipated along the shells, then that's what you would do. But in neither case do you agree well with the data. But if you start putting a wave drag in, then you get results like this one that are much closer. So you get closer to the world when you get wave drag, and our hypothesis is that in this model you're not resolving the braking, so you still have to put some damping in. This shows the same results in globally averaged amplitudes, and so that's with no wave drag. That's Richard Ray's real world results. This is with various strengths of wave drag. And you see that it also depends on the record duration. So we still need to understand this, but I think essentially what's happening is you're estimating an internal tide signal in a background of large eddies, and so it takes longer records to resolve that. So this is what, I have to go fast, I didn't realize you said I'm not too much time left. This is See, when I practiced this, it went a lot faster. This is a map of the supertidal motions in the steric SSH. So I think this is pretty valuable for altimetry because it's essentially showing how big is that signal. Just make a map, how big is it? That's in centimeters squared, so that's going to be a hard signal to remove from the altimeter. It's probably a lower bound as well because our model is not fully resolving that spectrum. I'll skip that. Internal tide incoherence. The French Polynesian Islands are a big generator of internal tides. They propagate towards the equator. This is what the total energy flux looks like, and this is what the fraction of incoherent flux looks like. So you're taking the total flux minus the coherence, that's the incoherent part. And what you see is that the energy flux still crosses the equator, but it actually becomes much more incoherent. What we show in that paper is that that is because you have a screaming equatorial jet here that decoheres the tides. The incoherent internal tides are also going to be a lot harder to pick out of the altimeter data because they're incoherent, they're not as predictable. This is a plot that was made last week showing the fraction of incoherence in altimeter data as determined from wavenumber spectra. You can't do it from frequency spectra, but you can look at the total variance and then take the coherent part out and look at the fraction incoherence, the fraction that's incoherent from altimeter data. This is from our model using a frequency spectrum method. Again, the western boundary current regions don't agree very well for reasons that we think are explainable. Basically, we don't believe the altimeter in those regions. But look at how along the equatorial Pacific and Indian Ocean there's a lot of agreement. So I'm really pleased by that because I think that means we can use these models to really understand the incoherent tides and how that matters through altimetry. I'll skip this. I'll just tell you very quickly. We've shown in here that nonlinearities are present and driving the spectrum. That's the point of that plot. I can explain the details if you're interested. Again, we made maps of how big the non-stationary component is. That matters because it's going to be hard to remove it from altimetry. Supertidal gravity, Garrett-Monk's continuum, also going to be hard. I'll skip these. Getting back to the last few slides, getting back to that first thing I talked about. So here's our first attempt to improve the tides using stuff from the data simulative literature. This is the error in our early simulations that I showed a lot earlier. This is if you do a better job on some of the dynamics. Now, if you hit the model with a bunch of so if you do 100 ensemble runs, 100 member ensemble runs of global 1/12 degree 41 layer HYCOM, and you hit them with these perturbations to the tidal forcing, and then you use the Kalman filter technology to get the optimal linear combination of all that, then you can beat the error down to this. Okay, so this is a lot better than this, and we hope that that'll lead to improvements in the internal tide. That still remains to be seen. There's still a lot of error in North Atlantic, and we think that is because of those resonances that I talked about earlier. There's a lot of big tidal resonances here which have a back effect on the open ocean. So what we've done is we've actually figured out how, not me so much, but we figured out how to do two-way nesting in HYCOM. And so you get better coastal tides in that sweet spot, and that actually feeds back onto the whole globe. And we're also trying to use adjoint technology to get better perturbations. I'll skip that. And so to summarize, we've added internal tides and internal gravity wave continuum in a small but growing number of global ocean models, beginning with HYCOM. The MIT model is now doing that, and it's bigger resolution for now. Wide range of applications, including planning for SWAT, and here's some challenges for the future. So how far into the spectrum can we get? What's the best way to go the rest of the way of the spectrum, downscaling to regional models or other methods? Is it actually possible, if you have a model like HYCOM, to predict the incoherent tides? If the data simulation technology puts the eddies in the right spot and the internal tides are reasonable, can you actually predict in a time-stepping way the incoherent part? We don't know, but we're going to try. Anyway, there are some other questions here, too. All right, I'll stop there.
Thank you, Brian. 2 questions.
The question in the back.
Thanks for the very interesting presentation. Actually, care most about the ensemble common filter scheme you used in the simulation for the tides. So to my understanding that you are using the along track SLA data to get a better representation of the tide?
No, in that case, what we did was we put in perturbations that were of the same general scale as large-scale barotropic tides, and then we compared the error maps against TPXO, which is Gary Egbert's barotropic tide. It was just about the barotropic tide. So we use the along-track altimeter data when we're interested in the internal tide, but if you're interested in the barotropic tide, you can use 2-dimensional models.
So it's about the tide that trigger the internal tide.
Well, that's right. So I mean, the Navy cares about the barotropic tide and the internal tide, and so the idea is if you can improve the barotropic tide, that will hopefully improve your internal tide. We haven't even had time to look at the second part yet, so we don't know whether that's true.
Thanks.
Yeah.
I was impressed by your moorings that you have validated with 1,600 moorings. Maybe we can discuss later, but I was impressed to how can you collect all this data and so with.
Well, Rob Scott, who is in Brest, actually originated this archive. We've done a few studies like this. We've compared tidal currents to thousands of current meters and low frequency potential energy, tidal, you know, just any combination you can think of, low, high frequency potential energy, kinetic energy. Yeah. But it is worth pointing out, again, not to pick on some other people, but you go to some SWAT meetings, they'll show a comparison to 1 current meter. Oh, look. I mean, come on. Get serious.
Okay. For your some results, you said the HYCOM results may be no, so MITgcm the result that is a little better than the HYCOM results. So do you think it is because of the MITgcm model have the non-hydrostatic model in it?
So the MIT model is definitely doing a better job on the internal gravity wave continuum, and I think it's just due to resolution. That global simulation is still hydrostatic. Yes, the MIT model does have the capacity to be non-hydrostatic, and we may take advantage of that in these runs I was talking about here. We might push these runs into non-hydrostatic, but the global simulation is actually still hydrostatic. That's just simply due to the expense. You know, it's already an incredibly expensive model. They ran it on 70,000 cores, and non-hydrostatic would make it even more expensive, so they didn't do it.
Well, it was the same question here, no? Yeah. So we are done. Thank you very much. So.